our group assignment in application of first-order differential equations, we will explain about Newton's law of cooling or warming. Newton's law. What is Newton's law? Newton's law of cooling states that the rate of change of the temperature of an object is proportional to the difference between its own temperature and the ambient temperature. Newton's law makes a statement about an instantaneous rate of change of the temperature. Newton's law of cooling is useful for studying an object heating because it can tell us how fast the object cools off. For our problem statement, Syahira decides to make a roasted chicken for her dinner. At 9 p.m., she took the chicken out of the oven, and its temperature was 300 Fahrenheit at that time. 15 minutes later, its temperature cools down to 200 Fahrenheit. The temperature of the environment is 50 Fahrenheit at that time. Objectives of this study is, first, to make people understand about Newton's law of cooling or warming. Second, to show people that application of first-order differential equation is easy. Third, to show people how to measure or solve problems regarding the applications of Newton's law of cooling or warming in daily life.
Next, I will explain about formulation of model and method of solutions. For this question, we will use separable equations. Step 1, we need to separate the information in the equation into uppercase T, which is temperature of object, Tm, temperature of surrounding, and lowercase t, which is time. Step 2, we need to apply the general formula of Newton's law of cooling warming with K is a constant. So the formula is d uppercase T over d lowercase t equal to K multiplied with T minus Tm. Step 3, we need to separate the equation where one side is dependent on uppercase T and other side is dependent on lowercase t. So the formula is 1 over T minus Tm d uppercase T equal to K d lowercase t. Step 4, we need to integrate both sides. So the integration of 1 over T minus Tm dt, we will get ln T minus Tm, and the integration of K dt, we will get Kt plus T. So in order to get rid of ln, we need to multiply with exponent in both sides. Then we need to let EC equal to A, and the last equation we will get T minus Tm equal to AE power of Kt. Step 5. Since the object is cooling down to the surrounding temperature, we need to understand that the temperature of the object will always higher than the temperature of the surrounding environment, where T greater than Tm. Therefore, the simplified equation should be T equal to Tm plus AE power of K.
Next, we continue with result of solution. For question A, prove that the temperature of the chicken at any time T is T equals to 50 plus 250 e power of negative 0.0341 T. First, we need to know general form of Newton's law of cooling and or warming. That is dt over dt equals to Kt minus Tm. Then substitute the temperature of surrounding, that is 50, in the general form. So it will get dt over dt equals to Kt minus 50. Then we integrate both sides. So integrate 1 over T minus 50 dt equals to integrate K dt. So the final answer of T, that we will create a equation. That is T equals to AE power of Kt plus 50. Then apply the conditions given to find values of A and K. Substitute time equals to 0, temperature equals to 300 in the equation. So the equation will be AE K 0 plus 50 equals to 300. So A equals to 250. Then values of K. Substitute time equals to 15, temperature equals to 200, and A equals to 250 in the equation. So the equation will be AE K 15 plus 50 equals to 200. Then E power of 15 K equals to 3/5. Then we put ln in the both side. So the final answer of K is negative 0.0341. Then substitute the values of A and K into the equation. A is 250, K is negative 0.0341. So the equation will be T equals to 50 plus 250 e power of negative 0.0341 T. Therefore, the equation is proof. Next, question B. How long will it take for the chicken to cool off to 60? Then we substitute the value given in the equation. So we will get 50 plus 250 e power of negative 0.0341 T equals to 60. Then we solve for T. E power of negative 0.0341 T equals to 1/25. Then we put ln in the both side. So the final answer of T is 94.40. So it will take approximately 94.40 minutes for the chicken to cool off to 60. Next, question C. What time is needed for the temperature of the roasted chicken to be 85? First, substitute the value given in the equation. So we will get 50 plus 250 e power of negative 0.0341 T equals to 85. Then, solve for T. E power of negative 0.0341 T equals to 7/50. Then, we put ln in the both sides. So, the final answer for T is 57.66. Therefore, it takes 58 minutes for the roasted chicken to have a temperature of 85. Next, question D. What is the temperature of the chicken if she decided to do her homework and leave it for another 20 minutes? Time is equals to 20 plus 15 equals to 35. The value of 15 we get from the question. So next, we substitute the value of time equals to 35 in the equation. So, the equation will be T equals to 50 plus 250 e power of negative 0.0341 bracket 35. So, the final answer of temperature is 125.8. Therefore, Syahira will be able to eat the roasted chicken when the temperature is 125.8.
Discussions. First and foremost, for the questions A, to prove on how we get temperature T at any time T equal to 50 plus 250 exponent negative 0.0341 T, is we use separable equation and then integration to simplify the general form of Newton's law cooling and warming. Next, from the calculation of the questions B, Syahira needs to wait 94.50 minutes for the chicken temperature to drop to 60 degrees of Fahrenheit before she can eat it. We can see that the temperature slowly decreases over the time and almost reach the environment temperature. The environment temperature must be lower than the chicken temperature, and it follows the Newton's law of cooling. And for the question C, the roast chicken need to approximately 58 minutes or 1 hour if the temperature need to be 85 degrees of Fahrenheit. And lastly, the temperature of the roast chicken will be 125.8 degrees Fahrenheit or 52.11 degrees Celsius if Syahira decides to do her homework and leaves it for another 20 minutes. So this will make the roast chicken to be more delicious if she still eat in the warm condition. So from the case study above that we can see, so we can conclude that all of the studies above from the Newton's law of cooling and warming is very useful in our daily life and it can be applied to any problem of matters. As for our problem, the temperature of the roast chicken, the time taken to cool down and the temperature to be high can be solved by applying this law.